Hello everyone, today we're talking about geometric sequences, section 10.3 in our book. So before we go ahead and get into any examples, I want to quickly explain a geometric sequence formula. So similar to our arithmetic sequence formula, our geometric sequence formula, so the nth term, however many terms we're looking for, a sub n, is going to be equal to a, my starting term, so same as before, but now we're multiplying. So geometric sequences, we're multiplying by a number to get from one term to the next instead of adding or subtracting. And by multiplying, we can also be multiplying by a fraction. So that's why they call R our common ratio, right? So because you could be multiplying, you can see in this example here, we're multiplying by 4, but you could just as easily be multiplying by 1/4. Right? So we don't think of geometric sequences as dividing. We think of it as multiplying by a ratio. Right? So this one is obviously 4 over 1. So we're multiplying by a ratio of 4. And then you take that ratio and you raise it to n minus 1, n of course being the term you're looking for. Okay, so similarities to arithmetic sequence, general term, first term, ratio that we're multiplying each term by, and then to the nth term minus 1. So another example here, if I have a common ratio of 4, starting term of 2, and they want me to find the nth term. So that is this geometric sequence, right? Because I've started at 2, my ratio is 4, that's what I'm multiplying each term by. I can find the 9th term by plugging into my geometric sequence formula. So let's use that formula to first find the nth term, and then find the 4th term. So a sub n equal to a times r to the n minus 1. Okay. So I'm going to leave it in terms of n. I know this is 3. I know that this is 2. Sorry, not r. Rather 2 raised to the n minus 1. So that's as far as I can go. Then if you tell me which term I'm looking for, I can plug in for that term, obviously plugging n in for the term number. So that is my nth term. Now I want to find the 4th term. Okay, so to find the 4th term, I'm really looking for a sub 4. That's going to be equal to 3 times 2 raised to the 4 minus 1. And so that is 3 times 2, 4 minus 1 is 3. So 3 times 8. We can see that the 4th term of this geometric sequence, 24. Makes sense, right? If we're starting at 3 and our common ratio is 2, well, 3 times 2 would be 6, times 2 would be 12, and then the 4th term, 24. So that one's pretty easy to get to the 4th term, but when we get maybe further terms out or more complicated numbers, you're definitely going to want to know how to use the geometric sequence formula. And the geometric sequence formula is another one of those formulas that are going to be given to you on the final. Now, first is determine the common ratio, find the 7th term and the nth term. So the first thing is finding the common ratio. Here we're seeing that this time by ratio we're going to mean a fraction, right? And how do I get from 1 to 1/3? Well, I'm multiplying by 1/3. How do I get from 1/3 to 1/9? I again multiply by 1/3, right? And I'm not thinking about this as dividing by 3. I'm thinking about it as multiplying by the ratio, multiplying by the fraction 1/3. So now I know my common ratio. They want me to find the 7th term. So a sub 7 equals, my first term was 1, right? That's the first term in my sequence, times common ratio we found was 1/3 raised to the 7 minus 1, the n minus 1. So I take and solve 1 times 1/3 raised to the 6th. That is 1 times 1 over 729. So the 7th term would be 1 over 729. And if you consider this process out, you would see that you would get to 1 over 729 for the 7th term. And finally, they want us to find the nth term. So a sub n equaling 1, because that's my first term, times the ratio 1/3 raised to the n minus 1. That's as far as we can go, because we're not sure exactly what term they want us to look for. Partial sum of geometric sequence formulas. So just like with the arithmetic sequence formula, we have a partial sum for the geometric sequence formula. Okay, so we can jump out to the sum of a certain number of terms. Okay, this sequence though, and if this is hard to read, you'll see it attached in the PowerPoint. Okay, so we're going to take our first term times the ratio of 1 minus the rate, or the common ratio, raised to n, whatever term we're looking for, over 1 minus the common ratio. And we have to keep in mind that the common ratio can't be 1, right? Because that really wouldn't make sense, because we'd just be multiplying by 1, so our sequence wouldn't be growing, okay? And also 1 would make this denominator equal to 0, so it obviously can't be 1, but there's another reason why 1 doesn't make sense, because we would just be multiplying by 1. Our series wouldn't be changing. So let's go ahead and use the partial sum to find the 5th partial sum. So again, I'll write general terms bigger on this slide. Hopefully we can see it. So A1 times 1 minus the rate raised to the term we're looking for over 1 minus the ratio. I should have said ratio. And that is our partial sum for geometric sequences. And this will be given to you on the final, so you don't have to memorize that either. You just have to know how to use it. Plug in what we know. I'm looking for the 5th, that's an S, that's 5, 5th partial sum of this geometric sequence. Okay, I know it's geometrics because they're telling me my ratio, my R is 0.7, and if you think R arithmetic, they'll say the D is 0.7, right? Because that would be a common difference. So that's special thing you should be able to realize is that if they give us our R, we know that stands for ratio. It's a geometric sequence. As opposed to D, that stands for the common difference. That's an arithmetic sequence. So continuing on, I know my first term is 1. Then I plug in what I know, 1 minus, my ratio is 0.7. I'm taking 0.7 and raising it to the 5th power, because that's the partial sum I'm looking for. I'm looking for the 5th partial sum, and then 1 minus 0.7. Okay, continuing on. This simplifies to 1 times 1 minus 0.16807 over 0.3, right? 1 minus 0.7 will give us that denominator. Simplifying a little bit further, we're obviously getting 1. I'm leaving the 1 out in front just so we do not forget to multiply by that first term. We obviously know multiplying by 1 isn't going to change it, but I'm just keeping it in generalities. So if I simplify, I get 0.83193 over 0.3. And 1 times that is 2.7731. So the partial sum, so the sum from the first term, which was 1, to the 5th term, I didn't even need to find the 5th term, but the sum from the first term to the 5th term, when I add up those sums, I get 2.7731. And the question may ask for you to specifically round. If not, try to keep it as exact as possible. Okay, next we have a patient woman who wishes to become a billionaire. She decides to follow a simple scheme. She she puts aside 1 cent a day for the first day, 2 cents the second day, 4 cents the third day, and doubling the number of cents each day. How much money would she have after 30 days? So they first want us to find out how much money she'd have after 30 days, and then how many days it would take her to become a billionaire, right? Her wish. She wants to be a billionaire. So what we know, I know my common ratio is 2. Right? I'm multiplying by 2. Each term I'm multiplying by 2 to get the next term. I know my first term is 0.01, right? I'm talking about money, so 1 cent is $0.01. And then I should know my partial sum formula. So that's basically what I'm doing, right? I'm figuring out how much money I'm going to make after 30 days. So I'm adding it up. I'm finding the partial sum from the first term to the 30th term. Okay, so I'm really looking for the 30th partial sum. That's equal to 0.01, 1 minus. Then I take my rate. I raise that rate to n, so the 30th power. And I divide that by 1 minus 2. Right, 1 minus and 2 being the ratio. That gives me 0.01 times negative 107,374,183 over negative 1. Obviously a negative divided by a negative is going to make it a positive. And when I multiply that number by 0.01, I get $737,418.23. That's how much money she has made after 30 days, right? I found the partial sum from the first day to the 30th day. And that's just by doubling how much she's saving each day. But then the question asks for, they want us to figure out how long it would take her to become a billionaire if she kept saving double each day. So what I'm looking for is, I know that's 1 billion. I know my partial sum has to total up to $1 billion, right? Because that's her goal. She wants to be a billion. I also know that I started with 1 cent. Let me write that a little bit neater. I know my ratio is 2. What I do not know is my n. I do not know how many terms I have to go and add up, right, to get to $1 billion. So I'm going to solve this equation for n, and then it'll tell me how many days she had to keep this up until she reached her goal of $1 billion. So the first thing I would do is divide by 0.01. When I do that, I add 2 extra zeros, so I get to 100 billion. And that's equal to this. If I simplify this a little bit, I can also see that 1 minus 2 to the n over negative 1. Okay, then obviously multiply by negative 1 to get the negative 1 off the bottom. That'll negate this side. That's going to be equal to 1 minus 2 to the n. Okay, then I'm going to want to subtract 1, which is going to be 100 billion and 1. Okay, then I can divide both by a negative 1 to get rid of the negative sign. Right, so I don't even really need to do much to get rid of the negative sign. And now I need to solve for an exponent. So I got to think all the way back to chapter 4, right, when we did exponential equations. So what I need to do here is I need to take the log of both sides. So if I take the log of 1 billion and 1, I'm not going to keep writing it, we understand it's 1 billion and 1, that's equal to the log of 2 to the n. Remember rules of exponents, I can bring my n out to the front. So what I'm really doing is I'm taking the log of 1 billion, 100 billion, and 1, and I'm dividing that by the log of 2. And that'll give me how many days it took her to get to $1 billion. And if you go ahead and solve this, your calculator will spit back to you 36.54 days. If she kept up doubling how much money she saved each day, take her 36.5 days to reach her goal of $1 billion. Maybe not realistic, but we could solve for how many days it would take her doing that savings scheme. Okay, so just to recap, because that one was quite a long one, we first found the partial sum of 30 days. We found out how much money she would save after 30 days of doubling her savings each day, and then we found how long it would take her to become a billionaire. Final term in this section is an infinite geometric sequence. Right? So if a geometric series goes on forever, right, we're just multiplying by the ratio over and over. What if we want to figure out how much that sum adds up to, right, as it would go to infinity? So this, again, if it's tough to read, this is attached in the PowerPoint, right? But this equation, the sum equals your first term over 1 minus your ratio. That'll actually tell you what your total series would add up to as you go all the way out to infinity. So what it would approach, right? Kind of like a limit. So find the sum of this infinite geometric series. So again, our
students, if you are not with the teacher or testing or in some after-school activity, please.
Okay, so again, our infinite sum, we don't need to know what term we're looking for, right? So it's just S, because we're not looking for a specific term. This is an infinite series, it never ends. So it's just S equals A sub 1 over 1 minus R. Okay, and we can see here, well, what are we doing? What's our common difference? What's our common, well, not our common difference, what's our ratio? What are we multiplying by each term? Well, to get from 2 to 2/5, I'm multiplying by 1/5. Right, so this is my first term was 2, my second term was 2/5. If I multiply by 1/5 again, I'm going to get the 2/25. So the sum of the infinite series now, we want to add all these terms up in our geometric sequence. So my total sum is equal to my first term, 1 minus my ratio of 1/5. Okay, so my sum is going to be equal to 2 over 4/5. And if I compute that, I will see that even all the way out at infinity, right, my numbers are going to get much, much smaller, my fractions are going to get much, much smaller, so the largest my series will add up to is just 2.5. So I started at 2, the largest I'm going to get to is 2.5, so it's kind of like my limit of this geometric sequence is approaching 2.5. Okay, so go ahead and try the example problems that accompany this in the PowerPoint. Give them your best shot using what we've learned here, and then we'll go over them in class tomorrow.